अनम्यूट कर दो. It's my machine, so.
In engineering,
Just go back.
I design algorithms to simulate complex physical and engineering systems on a computer. We implement them in the real world to predict real world phenomena, for instance in astrophysics, in climate modeling, in geophysics, in engineering. I'm Siddharth Mishra and I'm an applied and computational mathematician. I derive great satisfaction from being able to understand complex physical phenomena in mathematical terms. When I was a teenager, I was finishing high school, I wanted to be a physicist. After finishing my undergraduate studies, I had a much more attractive scholarship to do mathematics, so I just stuck to that. Even though it was just random, I think it was a very good choice. I'm very passionate about my research, about tackling hard questions, about communicating the excitement of doing science. I'm also passionate about collaborating with physicists, with engineers, with biologists to solve problems which arise in the real world.
Ujjwal, use the mic because someone in IIT Bombay is supposed to listen.
Okay, so it's my pleasure to introduce today's speaker, winner of this year's Infosys Prize in Mathematical Sciences, Professor Dr. Siddharth Mishra. Well, that's how they write it in Etheo, right? So after finishing his graduation from Utkal University in Bhubaneswar, in 2000 he joined TIFR. More precisely, he joined a program run jointly by IISc and TIFR and received a PhD degree in 2005 under the supervision of Professor Adimutty. And then he went to CMA, Center of Mathematics for Application at the University of Oslo as a postdoc for 4 years, 2005 to 9, and then subsequently went to ETH Zürich as an assistant professor for 2 years, 2009 to 11. And then he became an associate prof in 2012 and a full professor in 2015. So I think in between he was in Oslo for a brief time. So Professor Mishra is the recipient of many awards such as Richard von Mises Prize in 2015, JLL Awards, Jackie Lyons Awards in 2018, ICIAM Colas Prize in 2019, and the most recent one is the Infosys Prize in 2019. Besides, he was also an invited speaker at the ICM held in Rio, Brazil in 2018. So coming to his contribution, Professor Mishra has made several important contributions to many aspects of applied mathematics, and I will mention some of them. So indeed, most of the real world problems need numerical solution because of the inherent difficulties attached to this kind of problem. And this in a way forces applied mathematicians to develop computational methods, for example, algorithms that yield approximations, to analyze their effectiveness and finally to implement them. And sometimes these numerical calculations can provide a clue as to the qualitative behavior of the actual solution. So in that context, he has designed stable schemes for approximating the solutions of hyperbolic systems of conservation laws. providing some of the first examples of numerical methods for such systems with rigorous stability properties. He has proved, or he has provided a proof of the stability of certain common scheme used in fluid mechanics and image processing. Professor Mishra's schemes are being used in astrophysics for calculations of exploding supernovas, to propagation of oven waves in the solar chromosphere, and climate studies in the simulation of dynamics of clouds. In another contribution, so it is well known that in all real life models, initial data are often not precise, and perhaps they are statistical in nature. So thereby one needs methods that propagate the data forward and provide an answer to them. In that context, he recently developed the concept of statistical solution for the system of conservation laws in multiple dimension, and with the aim that this will shed some light to the uniqueness, outstanding uniqueness problem for such systems. And these problems are very difficult because typically solutions are not smooth and develop shocks that needed to be tracked accurately. And such problems are quite generic. For example, they occur in aerodynamics, in weather prediction, and many other daily life problems. And Professor Mishra has made outstanding contributions by constructing numerical methods, analyzing mathematically their effectiveness, and implementing them to solve concrete real-world problems. So on behalf of TIFR CAM, I really want to congratulate again Professor Mishra for being awarded this prestigious Infosys Prize in Mathematics in 2019. So today he is going to talk about statistical perspective for fluid dynamics problems, namely Euler and those. So it's all yours.
Okay, so first of all, am I audible? Yeah. So let me just put up my talk and then we start from there. It feels very artificial to look at myself. Okay. So let me start by saying a few words about, first of all, I'm honored and delighted to receive this prize. But for me, it's a great pleasure and also a lot of pride and emotion that I am giving this lecture in front of people who have shaped me more than probably most other occurrences in my life, which is my teachers at the TIFR Center. Many of you are here, and I am truly, truly indebted to you. I remember when I came in 2000, we were still in the IISc campus, and I went to Professor Adimurthy's office and Professor Vasudevamurthy's office, Vaninathan, Shrikant, and I was completely at odds. What's going on here? Means I was to some extent even scared. Am I good enough to be in such a place? And then it was my seniors at that time, Sandeep in particular, who helped guide me and also train me mathematically. This was a unique place that we had, that people interacted with each other. There was no difference between faculty and students. There was no difference between students of different years. Sandeep, Prashant, they were my seniors, and there is some age difference between us, yet they would spend time, they would ask me questions, they would answer my questions, and afterwards it was a growing community. We had my juniors, Harish is here, and some others. Praveen was also a student at IISc at the same time. We had the same courses, and it was one of the best periods in my life. And I think the reason for that is not only you learn so much, but you learn in a very different way, not just from the class, but just by talking to people and by interacting with people. You learn a lot. We had very good visitors coming in. It was a very dynamic environment. And I think it was Vasu who told me this at some point that I remember, which has remained with me, that when you are at TIFR Center, you are not a student of just Adimurthy, you are a student of the whole center. I think you said that to me, and I really felt like that. Everyone was very supportive, and this includes the staff, you know, Pramila, Veena, all the staff of TIFR Center. It was a very lively place, and I must say that I miss it. and I've been in different continents, in different countries, in different contexts, I sort of miss this rich, not just intellectual, but I get a very rich intellectual environment at ETH, but this sort of holistic environment is really missed. And I hope that the students of today share some of that atmosphere that we had. And so it's difficult in mere words to express my gratitude, but this is what I wanted to say. Nevertheless, let me start with my talk. So the Infosys Science Foundation wanted me to give you a very catchy title, but my contents, I had a much more mundane title. My contents are still the same. So let's get straight to that. So the point about fluids is that they are all around us. So in the morning when I brush my teeth, I see the tap water forming a hydraulic jump. When I walk out of my house, I see smoke coming out of the neighbor's chimney. I look at the clouds, and from my office that you saw in the video, I have a view towards the Limmat River. I see it flowing very gently most of the year, but very fast after the alpine snow melt. So fluids are all around us. So wherever we look, even in this air in the room, is a fluid. But from a more serious perspective, if you want to design efficient aircraft, or if you want to predict the climate, or if you want to understand how stars are formed, and many different contexts, the behavior of fluids needs to be understood. And in mathematical terms, we have to talk about concrete models, how we understand them. So it's perhaps surprising that despite this immense diversity of phenomena that arise in fluid flows, that a single equation possibly serves as sort of a master equation, at least for Newtonian fluids. And this was derived by Navier and Stokes 200 years, practically to 150 years back. And these are the compressible Navier-Stokes equations, which I show you here. Rho is the density, U is the velocity field, so it has the same number of components as dimensions. P is the pressure, E is the total energy, and the left hand side of the equation is transport, the right hand side of the equation is diffusion. I don't write the full system, just a simplification of it. And there's one interesting non-dimensional constant that comes out, which I denote here by Re, and at least some of you can guess that this is nothing but the Reynolds number. So this is just a constant, a non-dimensional parameter, which is named after Osborne Reynolds, and it measures the sort of relative strength of the two terms. I told you this is transport, this is diffusion. How do these things stack up together, right? And you can go and measure it. It has a concrete formula, you can go and measure it. And for instance, if you're a swimmer, then your Reynolds number is approximately 10,000. We are in India. Cricket ball, it's 150,000 for a fast bowler. For a spinner, it's a little bit less. Then in an aircraft and in clouds, we are talking about some millions to some billions, about 10 million to 10 billion, let's say. And in astrophysics, these numbers are truly astronomical. The point that I'm trying to make is there are quite a lot of flows where this number is very large, right? So in principle, we can set it equal to infinity, and just formally doing that will mean that these terms are going to drop out. Diffusion sort of gets out, and it's purely transport. It turns out that these equations were derived even earlier by Euler in 1757. These are the compressible Euler equations. Euler is Swiss. It's an interesting coincidence. And these are the equations here. They represent the conservation of mass, of momentum, and of total energy. The total energy is defined by equation of state. So you have kinetic energy out here, and the pressure defines sort of the internal energy, at least for an ideal gas equation of state. It turns out that there is another limit lurking in the background, and this is realized if you look at a non-dimensionalization. All the time you have to non-dimensionalize these, and another number comes in, which is denoted by m here. It sits in front of the pressure in the momentum equation, and in front of the kinetic energy in the equation of state. And this term, as some of you might have guessed, is the Mach number. It's named after Mach in the 1880s. It's a non-dimensional parameter which measures the relative strength of the flow with respect to the sound speed. Again, we can go and measure it. So in a slow flowing river like the one in Zürich, it is 10 to the power minus 5. In the Brahmaputra, it's more 10 to the power minus 3 when it comes down from the Himalayas. In the clouds, it is between 10 to the power minus 3 and 10 to the power minus 1. Aircraft, this is order 1. Right? When we fly, it's like Mach 0.8. Astrophysics, it's all over the place. But there are quite a few interesting flows where this number is very small. So it makes some sense to look at it when m is equal to 0. Now the asymptotics, it's not straightforward. There is a little bit of asymptotic expansion to be done. But with a little bit of work, one arrives at what are called the incompressible Euler equations. so which are written here. So this is the momentum conservation, and the continuity equation simply reduces to the fact that the velocity field is divergence free. So compressible Euler and incompressible Euler, they form some sort of a continuum, and this is what I am going to talk about in this particular lecture. I will talk about different aspects of these equations. It turns out that both these equations can be written in a very compact form as a nonlinear PDE or a nonlinear systems of PDEs. These are called systems of conservation laws. So here is your PDE. U is the vector of unknowns. Think of it as the density, the momentum, and the total energy for the Euler equations, and F is a flux function. Compressible Euler equations are prototypical examples of what are called hyperbolic systems of conservation laws. So there is finite speed of propagation, the solutions are waves which move at a finite speed. It turns out that the incompressible Euler can also be written in the same form. It's not so straightforward, but all that you have to do is to project onto the first equation onto divergence free fields, do what is called a Hodge projection. This term is the same, this term drops out when you take the divergence, when you take the projection of a gradient, it is 0, and this term becomes non-local, because when you project you get a non-local operator, a sort of an integral kernel. So this is a non-local flux, and because of that there is an infinite speed of propagation. So that's the big difference between the compressible Euler and the incompressible Euler, the speed of propagation, which is not surprising, because if you look at the Mach number, so to let the Mach number go to 0, one way is to let this guy, the sound speed, go to infinity. So this is where, and this is the speed at which propagation happens. As a result, you have infinite speed of propagation. Nevertheless, it's a continuum. As I said, that the Mach number goes to 0, there is a continuum there. So these are systems of conservation laws. There are many other interesting examples of these, and these are PDEs. So if you want to understand PDEs, and all my training in PDEs was with people here, some of them also looking at us from Bombay, I think. And the point about PDEs is you have to talk about solutions, and the solutions need to have certain properties, and this is what I use with the Latin phrase desiderata, desired properties. The first set of properties which I learned here at the center were due to Adama, which says that you want to look at well-posedness of global solutions. So the questions are, does it exist globally, is it unique, is there continuous dependence with respect to data? But I have moved here out of here for 15 years, and in these 15 years I have realized that you need 2 more criteria which I put on the list. This one is computability. So not only do you need well-posedness, but the solution framework that you are designing, you should be able to, in principle, design numerical methods which are going to approximate them efficiently. And since the equations come from physics, the solution should somehow correspond or encode the physics in it, right? There are some observations, some experiments, you should be at least consistent with that. So these are the sort of desired criteria, and the question is what sort of solution frameworks fit those desired criteria, right? This is the question. So I start with this. The first thing that you can do is to look at classical solutions, right? These are differential equations and there are derivatives. So let's look at functions which are differentiable. So these are classical solutions, at least almost everywhere differentiable. Now I start with the incompressible Euler equations, and there is a dichotomy here, or a difference, because in 2 space dimensions, if you start with smooth initial data, then one can prove rigorously that there are smooth solutions. For instance, Udovich could be considered a result like that. For all time there are smooth classical solutions. In 3D, on the other hand, you don't know this. So even if you start with smooth initial data, it's unclear at the moment whether the solution remains smooth or whether there is a blow up globally in time. And why is there a difference? Because if you look at the equations, you don't see any 2D, 3D variation here, right? Where is the difference coming from? To look at the difference, we have to look at the vorticity. So the vorticity measures the rotationality of the flow. This is omega, the vorticity, the curl of the vector field. In 2D, this is just a scalar. And because of that, you see this is a 2D equation. It's a pure transport equation where transport happens with a divergence free field. And because of that, there are lots of estimates that you can prove. In particular, you can prove a maximum principle very easily. And these are sort of tools that you prove global existence and uniqueness with. In 3D, on the other hand, it is not like that. There is a pesky term on the right hand side. It is transport on the left hand side, but on the right hand side there is a very pesky term. This is a source term, it's called vortex stretching by physicists. And in fact you can see that if you just multiply with omega on both sides, then this is it requires the gradient of u. It's a function of gradient of u. We don't know the regularity of u, so the regularity of omega depends on the regularity of u, which depends on the regularity of omega. So there is this kind of an interaction, so it's unclear at the moment. So this is the situation for the incompressible Euler equations. Needless to say, even in 2D, where we have global solutions, the interesting classes of initial data, for instance vortex sheets, which the initial data itself is not a differentiable function, it's in fact a measure. So then these are the sort of limitations. But for hyperbolic systems of conservation laws, it's even worse or better, I don't know, depending on the perspective, because here, even if you take the simplest example of these equations, the so-called Burgers equation, just a scalar equation, you start with smooth initial data, and then you see in finite time the formation of discontinuities or shock waves. So there's no chance of getting classical solutions for the compressible Euler equations of systems of conservation laws. So what do? Most of you are students, all of you will learn this. We have to interpret the equations in the sense of distributions. We have to look for what are called weak solutions. So instead of considering the equation pointwise, what we are going to do is we multiply with the test function, smooth one, and then integrate by parts. The equations are in the divergence form, so you can throw the derivative by integration by parts, and you get this integral identity, which is completely well defined as long as your function is integrable in some sense. But of course, the issue with weak solutions, and this is also true for the incompressible Euler equations, they are in the same form. The issue is that these weak solutions are not unique, and you need some additional conditions to enforce uniqueness. These conditions are called entropy conditions because they are supposed to mimic the second law of thermodynamics, and this is the sort of form. So you have a convex function, and then in addition to this entropy, this identity, these guys have to satisfy an inequality because the entropy, mathematical entropy, has to decrease in the sense of distributions. And an example of an entropy is for the incompressible Euler equations is the total energy, the kinetic energy. The density is 1, so you can think of it as the kinetic energy. And this is what we think, or we thought, is the right notion of solutions. So let's try to see if entropy solutions are well posed in the sense of Adama. So these are some of the results. I'm not going into the details here. I'll start with the incompressible Euler equations. Remember that in 2D we already have smooth solutions, so this is not to be worried about. You can go much further because of course smooth solutions require smooth initial data. There's no regularization. So Delors in the 90s, he came out with a brilliant result that as soon as your vorticity is a measure, a signed measure, it has to have a sign, then you have global existence, which is far beyond the fact that your vorticity is a bounded function. So this was a big breakthrough. So vortex sheets exist globally, but the uniqueness is unknown. 3D, nothing. No smooth solutions, no weak solutions. We don't know anything about 3D, globally at least. What is recent though is that people have discovered that the admissible or entropy solutions for the incompressible Euler equations are not unique. They have been able to construct multiple entropy solutions or admissible weak solutions. It goes down to Schaeffer in the 90s, but recently it was exposed by and developed by Dillelis and Szekely-Hidi. It's based on what is called convex integration of Gromov from geometry of highly oscillatory approximate solutions. So we know these solutions are constructed and there are infinitely many solutions, which is pretty bad. What about hyperbolic systems of conservation laws? Here the situation is even worse. The results are only in 1D, so also with small data, but maybe that's a technical constraint. Only in 1D. If you go to 2D and 3D, we don't know anything about global existence, even though the equation was derived in 1757. So this is sort of an indictment of us as mathematicians, that it is 250, 270 years and we still don't know. And what we know based on the similar results to incompressible equations is that these entropy solutions are going to be non-unique. So there is no way you can have uniqueness of them, which is pretty bad, right? So, but remember the desiderata was that we needed existence, uniqueness, continuous dependence, and we can say that okay, this is bad situation for us, we don't know, and we know that they are not going to be unique. Okay, but what about these two? Maybe these are just mathematical artifacts and we will get around them somehow. Let's look at the concept of computability. So computability is related with the design or availability of good numerical methods, and let me give you very briefly some numerical methods for these equations just in 1D to illustrate for a system of conservation laws. So here is the grid, so you have to discretize. So this is space out here, this is time, And the object of interest are cell averages. Remember that my functions are discontinuous, they are not defined pointwise, so I need cell averages, and I evolve them. The evolution equation is the rate of change of cell averages is balanced by the fluxes. So this is just conservation. It tells you that the amount of stuff that changes in this cell depends on how much comes in and how much goes out through the boundary. To determine the fluxes, there is elaborate terminology and technology that I am not going to cover into, and you can do this as Ujjwal described at high order with good time steppers and so on. So there is numerical methods like this are available. Also for the incompressible Euler equations, they were similar methods. They were designed by Chorin. Because you have a divergence constraint, the divergence has to be 0. So you have to project onto divergence free fields, and this is done by projection, an elliptic projection. Another method which is very popular for the incompressible Euler equations is the spectral method. So it's a function, particularly in the torus. So you can expand it into Fourier series, and you project, you truncate, because finitely many, you are on a computer, you can't have infinite number of terms. So you project, you truncate, and you project onto divergence free fields. So action here is the effect of divergence free fields, and Tadmor realized some years back, 20-30 years back, that you also need some viscosity to stabilize this. So he added some numerical viscosity on the very high Fourier modes. So on the low frequencies, it's exactly as the equation should be. In the very high frequencies, at some scaling, it is some viscosity. And these methods are very popular, both sets of methods. And even in my research group in the last 10 years, as Ujjwal described, we have used them in many different contexts. For instance, in core collapse of supernovas, in waves in the solar atmosphere, Alfvén waves in particular, in the dynamics of clouds. So this is an observation, this is the simulation, very close to the observation with the incompressible Euler equations, larger dissimulation with classical flow past aerofoils, but the novelty is space-time adaptive grids, as you can see, at least in space here, and predicting tsunamis, simulating tsunamis in the Mediterranean. So all this has been done with the numerical methods that I just told you, and people here like Praveen do these kind of things routinely. So this is well known and very successful. But remember, this is not what we are seeking for, right? We are seeking for more than this. In particular, we have to understand what exactly are we computing with all these fancy methods. And this is, in numerical analysis, this is the concept of convergence. So this is the first question or essential question of numerical analysis. And you can formulate it like this. So you have a mesh parameter. This could be your mesh size, it could be a time step, it could be the number 1 over the number of Fourier modes, because number of Fourier modes goes to infinity that you truncate at. And for that you have a numerical solution. I call it as U delta. The question is, as you refine your mesh or you increase the number of Fourier modes, does this have a limit? And is this limit an entropy solution? This is the question of convergence, right? And it turns out that if you talk about rigorous results, this is really we are in a bad shape, at least for conservation laws, systems of conservation laws. It's available for scalar conservation laws, I would say 1D systems. However, and perhaps not surprising because the theory is what it is, for multi-D systems, we don't know if these numerical methods converge. I'll show you that we know more, but a priori we don't know. So what do? We still have numerical methods, we still have to compute. So what we do is some sort of an empirical demonstration of convergence. So I'll give you an example. We take a scheme, for instance this scheme, arbitrary high order scheme that Ujjwal spoke about, and we take your favorite problem, your benchmark problem. So in this case it is a compressible Euler equations in 2D on a torus, so periodic boundary conditions on the square, and I take what is called a short shock tube. It's just a shock tube that opens up, and I compute it on a sort of sequence of grids 128, 256, 512, and to see if it converges, to the eye it clearly converges, but to test that I just take successive differences, and then you can see that as in L1 at least it's a Cauchy sequence, so it has to converge. And based on examples like this is the simplest, but more complicated examples can come in. I take the same scheme and try to compute a realistic problem. For instance, I am very fond of this example because it comes from astrophysics. It's a big simulation. It's a Rayleigh-Taylor instability on an exoplanet, fairly realistic atmosphere. It looks very spectacular, but the point about this computation is that it's a very big computation. So there are 10 billion degrees of freedom. It's on unstructured grids, 10 billion degrees of freedom per time step, and it took 10,000 node hours on a top-end high-performance supercomputer, top-end supercomputer that I'll talk about. So it's a very expensive simulation, and what am I basing this simulation on? On examples like this. So to say that something like this, when the scheme works well, it will work well on something like this is admittedly a leap of faith, and it's a huge leap of faith, right? You can't guarantee that. So let's try to examine this a little bit more closely. So I stuck at this example, which is very instructive. It's called the Kelvin-Helmholtz problem, still two-dimensional, compressible Euler equations, periodic boundary conditions. All that I've changed is the initial conditions. The equation is the same, the scheme is the same, everything is the same, but the periodic boundary conditions. So you have this is the density in color. So you have low density, high density, low density, and in between you have a shear. So you have the velocity, wind going this way and that way, and even you have an interface like this. So this is a very well-known problem in fluid dynamics, and I repeat the same process. I compute on a sequence of grids, same scheme. So this is how it looks like: the density with 128 squared, 256 squared, 512 squared, 1024 squared, and as you can see, each time I'm refining, I'm getting a different picture. I'm getting vortices at different locations and so on. And this we have been able to compute at 16,384 squared. This is as refined as you can get under current precision, and each time you get a different picture. The vortices are different, newer and newer structures are coming in, and needless to say, when I take successive differences and try to plot the L1 distance, I get a flat line all the way up to 2 to the power 14, which is 16,384. So clearly in this case we don't observe any convergence, even though it was the same scheme where we observed convergence in another problem. So what's going on here? So of course there are some caveats here. It could be very slow convergence, it could be log-log, but if it does not converge to this resolution, it's useless in practice anyway. It's also observed for incompressible flows. This was just one example, and it's actually generic. Generic in the sense that as soon as your flow becomes unstable, turbulent, I'm using these terms carefully, you see this. For instance, okay, this problem clearly has that kind of features, but what is surprising is even this problem has these features. Remember, I have periodic boundary conditions, so I could have waited a little bit longer. This outer shock wave would have gone out, but then because of periodic boundary conditions, it would have come in, hit the contact discontinuity, and created similar structures. So everything, it's sort of generic in that sense. So because of that, computability is problematic, right? Because also it's nothing specific to this numerical scheme. Any numerical scheme shows the same non-convergent behavior. So now let's try to examine this notion of entropy or admissible weak solutions. As we know that there are no global existence results in multi-D and 3D for incompressible Euler, we know for a fact that they are not unique. We know that numerical schemes either don't converge in practice or converge very slowly. So given these basis points, it sort of makes sense to think of a new concept of solutions where this is an impasse, right? We don't know what's going on. So this is an impasse, and how do we resolve the impasse, right? So this was the thought process, and how do we resolve that? One idea, and I never thought I will ever put a picture of Paul Erdős in my slides, but somehow I figured out that he was talking about some similar things. So Paul Erdős, among the numerous things that he did, he pioneered something called the probabilistic method. So what is and in the words of Noga Alon, who wrote about the legacy of Erdős, let me read it, it's very nice. The probabilistic method is one of the most significant contributions of Paul Erdős, with numerous applications in combinatorics, in graph theory, number theory, and geometry. The basic idea is very simple. Trying to prove a structure, like a solution, with certain desired properties, you know what the properties are, one defines an appropriate probability space of structures and then shows that the desired properties hold in this space with positive probability. So instead of looking at the punchline for me is that when you're stuck in a deterministic problem, randomize it. This was somehow the take-home message from Erdős that I interpreted, and our problem is extremely amenable to randomization because in nature things are random. So what I'm going to do is I'm going to very slightly perturb this interface. I don't keep the same interface all the time, but in each experiment that I'm going to do, I'm slightly going to perturb the interface, and let's try to do that. Remember, for a single experiment, this was the picture, no convergence. This is sort of the differences between them. I take two of these tiny initial perturbations and then average the result. So this is the average here, and you can see that again nothing has changed really. If I take 8 of them, I start having some averaging, things are averaging out a bit, and you can start seeing that it's less complicated than before, still not convergent. If I take 64 of these realizations, then I start seeing convergence. At the mean value, it starts getting convergent. And finally, if I take 1024, so a lot of experiments, then you can see a very, very neat convergence. Okay. So this shouldn't come as a surprise to anyone who knows engineering or fluid dynamics or chaotic dynamical systems, that averaging helps, ensemble averaging helps. Even though the individual realizations are pretty nasty, the statistics are well behaved. But that's not the point. This is known, right? So the point is, how do you incorporate them in a mathematical framework, and how do you work with it? So the first attempt that I made was just, I found out that this was already done by someone else, a very famous one, Ron DiPerna, in the 1980s, who passed away rather prematurely. And this is a concept called measure valued solutions. And there are also some fundamental contributions by Maida. So Young measures, the solution concept is that the solutions are no longer functions. There are the Young measures, and these are space-time parameterized probability measures. And actually, the first time I learned about Young measures was at the TIFR center, and it was Professor Vaninathan who taught me this when he was talking about compensated compactness. But at that, and calculus of variations, homogenization. At that time, the way we thought about it, or at least I learned from the course, is that Young measures represent weak limits of bounded functions, because weak limits and nonlinearities don't commute. So to characterize that, you need Young measures. But a more fruitful approach for me is the following, and this is what I am trying to represent in the pictures here. So a classical notion of solutions is fixed time. So these are snapshots. At each point in space, or almost every point in space, I have a value. At this point I have a value, one value, could be temperature, pressure, whatever. Now what a Young measure does is that at each point in space, it's not just one value, but it's a whole range of values. And it also gives you a probability distribution. So it tells you how likely that value is. So you think of it as a 1-point PDF, probability density function. So at a different point, it could be a different 1-point PDF. At a different point, it could be a different 1-point PDF. It could happen that at some point, it's exactly one value. So your function reduces to a Dirac mass at that point, and if it happens almost everywhere, you're back to your classical notion of a solution. So Young measures are generalizations of functions. In fact, they are closures of functions in certain topologies, bounded functions in certain topologies. So statistically, this point of view is more fruitful, even though they are completely equivalent. So DiPerna had already introduced these concepts, both for conservation laws as well as for the incompressible Euler equations many years, 30 years back. So what was our contribution? Our contribution essentially was finding an algorithm. I call it efficient, we can argue about that. Finding an algorithm to compute these objects. Okay, this is what DiPerna had not done. So what you can do is essentially formalize the algorithm that I already showed you, do a lot of experiments and take ensemble averages. So this is this ensemble Monte Carlo algorithm, and we proved in these papers convergence, rigorous convergence results. On Young measures, there is a very natural topology. It's a weak star. So, and what it amounts to is not just functionals. So of course, the individual function is not going to converge point-wise. Even functionals, integrals are not going to converge, but statistics of them, these are what are going to converge. So this is all rigorous. So we have a rigorous algorithm, a rigorous proof of convergence of these, and because of that, remember that this was a picture, but a mean value is just a different function g is identity here, and then you have the solution here. So you have the mean value, and this converges, and there's a rigorous proof of that. The variance, and the variance really tells you how much of stochasticity, how much of randomness is there in the system. That is also very nicely convergent. Again, there is a proof and there is numerical evidence of it. And then remember that Young measures are nothing but point PDFs, probability density functions. So I just fix a point somewhere here, and I calculate the probability density functions over different grids. So this is at 128 squared, 256 squared, 512 squared, 1024 squared. At least to the eye, they seem to approximate, represent the same objects, right? So this was very, very pleasing, very satisfactory. Now let's remember the contrast between them. So whenever the measure valued solution is a Dirac, you're back to weak solutions. So they're genuinely extensions. One is an extension of the other. Weak solutions, I think of them as space-time averages, because individual quantities, point-wise quantities are not defined, then we had all these problems with convergence and computability and so on. But for measure valued solutions, in addition to the space-time averaging, you do an ensemble averaging. Then you have global existence, because convergence of a numerical method is the same as a global existence result, and computability. That's great, right? So it almost feels like you have solved the problem. So this is what I spoke about 6 years back when I was here at the center. But very quickly we realized that there's a huge issue with measure valued solutions, and that is non-uniqueness. Remember, we need existence, computability, but we also need uniqueness. And why non-unique? So this is, it's completely, and it's generic, means it's not something specific that you have to construct. Just take Burger's equation and I just represent this. Take non-atomic initial data. Remember, your initial data is now a PDF, a probability measure. So here is a point at which this is the initial data, and this is all analytic. These are formulas. There is no numerics here. So here is one solution. So there is a shock going through. So probability measure shifts from 0 to 1. And in the other case, you have a rarefaction. So there is a very gentle movement of measure. They end up at the same place, but in between they are completely different. So these are two solutions for the same thing. So it's non-unique, period. So you have to do something about it. Surprisingly, despite this generic non-uniqueness, when we compute these solutions, we find that they are very stable. If, for instance, I change the nature of the perturbations, I change the type of perturbations, whether it's a uniform or normal distribution, you see you get the same mean, you get the same variance, and what is more dramatic is you take completely different numerical methods. One is based on one type of scheme, another is based on another type of scheme. You still get the same mean value and the same variance, modulo numerical errors. So this suggests that the numerical solution that we are computing is certainly not a generic measure valued solution. If it were, then it don't have these stability properties. So what you are computing seems to have some selection criteria that constrains the measure valued solution. The question is, what are these selection criteria, right? We need to understand that. And let me spend a couple of minutes on this. By the way, is someone keeping track of time? Because I don't know when you stopped and when I started. So, okay. It's infinite time. It's finite. Okay. Okay. Let's look at why are these non-unique. Let's try to think about it a little. Let me take the simplest possible situation here. We have a nonlinear scalar conservation law, because already it was non-unique there in one space dimension, which is written here. And remember, what does a measure valued solution do? By the way, I probably have skipped it, but what you do is that you integrate this function, this equation against the measure. So when you do that, you have an equation which tells you the evolution of the mean, and you have an equation which gives you a bound. This is entropy inequality, and this gives you a bound on the second moment. That's all the information that you put in. A measure valued solution, evolution equation for the mean, a bound on the second moment. But all of us know that if you know the mean value and the second moment, or a bound on the second moment, there are tons and tons of probability distributions that will correspond to it. Means they don't uniquely specify anything. However, I would be able to uniquely specify the measure if, instead of having just the mean and the second moment here, because S is a convex function, that's why it's second moment, I could put some arbitrary test functions. Then it will be like all moments, and then this measure can be better understood. So you can just do this formal calculation. This is completely formal, and then you yes. Yes, exactly. So even that is not enough. So this is really genuinely a large class of test functions, right? But then they will be, because this is not just moments. This is all possible continuous vanishing at infinity test functions. So then you take this, and then you have. By the way, I'll come back to the question about the moments soon, because there's some boundedness issue there. So then everything works. So the Young measure here is closed with the Young measure here. Everything is fine, except there is one term which is very pesky here. And to describe this, I have used some random field representation of the measure. We can always do that, formally at least. And what it tells me is that to specify this Young measure uniquely, I need to understand the probability. That's why there's a probability here. This is an integral over the probability space of how the function changes at the point x and a point x plus h, of course close by. But what I need is, in order to get 1 point statistics, I need information, conditional probability between the function at x and x plus h, and this is precisely what is called a correlation. So to specify a 1 point measure, I need a 2 point correlation. A picture helps. So you have a measure here and you have another measure here. but in order to determine this uniquely, any chance, I am not saying that that will determine it uniquely, but any chance you have to have information about joint probabilities. Okay, maybe you can do that and we can play this game. Now how are we going to determine the joint probabilities? Then you go back to the equation, you play the same game. To calculate the 2-point joint probabilities, you need the 3-point joint probabilities, you need the 4-point joint probabilities, and so on and so forth. And this is because of the nonlinearity. The nonlinearity forces us to look at correlations. If it is linear, we can escape that. And because of that, we need all possible multi-point correlations. So this is how it is. And this seems like a formidable thing, means all possible multi-point correlations. So some years back, I had a very good master's student who is a current PhD student, Samuel Lanthaler. And we decided to take on this challenge and say, okay, let's introduce all possible multi-point correlations. And to formalize this, we worked with Young measures, but we introduced what are called correlation measures. So these are Young measures. Remember, Young measures were 1-point statistics. Correlation measures are multi-point statistics, somehow multi-point correlations. And there is a formalism which I am not going into details. In particular, you need something called a diagonal continuity, which is some control of this correlation at small scales. This is a technical object called the structure function, which also comes in turbulence theory in a very natural manner. So there are these set of objects, and think of them always as this multi-point correlation, multi-point PDFs. Okay, so we can do that. This is a infinite family of objects, but the first surprise, at least to us, was that there is a intrinsic connection between this infinite family of objects and a single object. And that single object now is a probability measure, but on a function space, in this case P integrable functions. And there is a very precise way in which some sort of Fubini type theorem which holds between these two, but let me try to explain to you sort of pictorially what this representation is. Remember that I need my 1-point PDF, I need my 2-point correlations, 3-point correlations, all possible multi-point correlations. I say, I can prove that all these objects are completely equivalent to a single object, which is a probability measure, but on a function space. What does that mean? Well, it's not hard to assign a probability measure on a function space. Just think of this bunch of functions that I have drawn here. So all that I say is a certain probability, 0.2 of the green function, 0.1 of the red function, and so on. So it could be that one of them has probability 1 and the rest has 0, then you're back into functions. Otherwise, you put a probability measure on functions. So in this way, you generalize the notion of functions in a way, or solutions in that sense, but it's a probability measure on an infinite dimensional space, so it brings it its own difficulties. Okay, and here under some technical boundedness conditions which are very natural, this object probability measure in functions is determined by a set of moments, and these are the so-called correlation moments, correlation functions as they are called in physics. So these are these sort of tensorial moments. Okay, so these are sort of surprising. So there is a neat formulation on how to do this, but how do we relate this to our equation, right? Okay, we say that my solution, this is where statistical solutions comes in. These are time parametrized probability measures, but on a function space. Okay, and the way we are going to determine them is through their moments, because these guys, infinitely many of them, are going to specify this. How are we going to calculate this? These are just tensor products. So we start with smooth solutions. We take these are just at x1 and x2, 2 points. We write down the equation. We get this sort of linear nonlinear structure, and this calculation can be generalized rigorously from smooth solutions to weak solutions, from 2 points to all possible finite points, from scalar to systems, from what else? From functions to measures. And if you do this, then what you get to determine this probability measure in functions is this infinite family of PDEs, and each PDE takes place on a tensor product domain, finite dimensional tensor product domain, but it keeps on expanding the dimension of the domain. So this is, if you think in terms of statistical physics, those who know it, my Liouville equation would be an infinite dimensional evolution equation for mu t, my probability measure on functions, but these moment equations are what are called a BBJKY hierarchy. So there is a very precise way in which you can think of them, at least in terms of an analogy. So now my object that I claim is a reasonable solution concept is a probability measure on functions. So you have it initially, and then somehow the flow forces you to push it forward and satisfy these equations. And okay, this seems very abstract, means how are we ever going to find such an object? The first thing is that we should relate it with what we already know. What we know is that as long as it's a Dirac, a function reduces to a single function, then it's just a weak solution as before, or an entropy solution. And the first, remember that this is a hierarchy, so there are infinitely many new K's. The first member is a Young measure, just a classical Young measure of Diperna, and all the additional ones are correlations. So one way of thinking about statistical solutions is it's a measure valued solution, but on top of it we add all possible multi-point correlations. So a priori we add a lot of extra information onto measure valued solutions. So hopefully this is much stronger. So hopefully there is some chance of constraining this. So but how are we ever going to construct such an object, right? It's a probability measure on functions, not the easiest thing to deal with. But the first thing I'm going to claim is that we can compute this. This is the starting point, and we will compute this with exactly the same algorithm that we computed the measure valued solutions with. That's why the measure valued solutions are stable, otherwise we wouldn't have known that. So what is this algorithm? It's a very simple algorithm. It starts with the initial probability measure, and then you should know how to sample from it, which is a non-trivial problem. But if you can, then you just draw samples from this distribution, and then so the initial measure is approximated by this sum of Dirac masses. For each of these samples we can use, for instance, a numerical method or maybe some theoretical construction. You push it forward and you form what is called an empirical measure. Okay, so this is the empirical measure where you add this. It's exactly the ensemble averaging algorithm. You have all these objects, you club them together in an ensemble. So there are two parameters here. Delta is your mesh parameter, m is the number of Monte Carlo samples. They are related to each other. And now this guy is a probability measure on functions, and it's a candidate for my statistical solution. So I have to say that as in the limit process, as I refine my grid, as I increase by number of Monte Carlo samples, this object will converge to that infinite dimensional measure on infinite dimensional spaces. And now we talk about topology, right? Once we have convergence, we have to talk about which topology things converge. So there are two elements to it. So space, we have probability measures. So weak topology seems to be natural there. On time, we have some time continuity. I'm not going to be technically correct, precise in this talk. So we have some weak star topology. So weak in space, weak star in time. This is the topology. But these topologies are not easy to work with. You know, these are infinite dimensional objects. It's not easy to work with them. So the first theorem, which is in a couple of papers here, is we found sufficient, and later on we proved that they're even necessary, conditions for compactness in this topology, and these conditions are very natural. The first condition is that your approximations should have some uniform bounds in LP. After all, you are going to approximate an object in LP or a probability measure in LP, so you need some uniformity of the bounds. This is a typical a priori estimate that we get from the entropy inequality. And the second concerns the structure function. So this is the object which told you something about correlations at small scales. And this object has to go to 0. It always goes to 0. There's the definition of the structure function, but it has to go to 0 uniformly with your parameters. If these two things happen, if and only if these two things happen, we have compactness in this topology. And these conditions are much easier to check than working with random arbitrary test functions. This is a very technical, I'm pretty proud of this theorem. Nevertheless, so how can we now check whether we have convergence or not? So again, in these two papers, so we have numerical approximation. We need the numerical approximation to satisfy these two conditions, and as long as there is a discrete entropy inequality, it's straightforward to see that these uniform bounds are satisfied. It's just an a priori estimate. Then for numerical approximations of these problems, we have no control on the gradient. The gradient is going to blow up in whatever norm that, or most likely it's going to blow up in whatever norm that you're going to look at, but we have some control at the rate at which it blows up. So we have blow up rate, and this blow up rate is what I call is a weak PV bound, and this translates to an estimate on the structure function, which is this quantity which measures essentially local gradients or local differences at the grid scale or smaller than the grid scale. So at the small scales we have a precise control on the structure function. Large scales it does not matter, but we don't just need it at small scales, we need it at all the intermediate scales because the things have to go down to 0. So then it's not so easy to know what happens in the intermediate scales, so I had to put an assumption, and the assumption was about that the approximate solutions, they're going to scale from the grid size to a larger scale in a precise manner, but with the inequality, not a very precise scaling. And if this is there, using these two estimates, we find some uniform control on the structure function, and then we apply our theorem, and we know that this object converges. And this scaling assumption, it's not artificial at all, it's a very natural assumption. It actually goes back to Kolmogorov in the 1940s even, when he was developing his famous K41 theory of turbulence. What Kolmogorov realized is that he wanted some scaling of the solutions. He wanted a very precise scaling because there is some symmetry to the equations. We just want an upper bound, we are not, and this upper bound is a relaxed version of the Kolmogorov scaling. This can also be formulated in terms of what is called the energy spectrum, which is a condition of the Fourier transforms. The energy spectrum tells you how many Fourier modes are there at a certain wave number, or what's the energy of the Fourier modes at a certain wave number. And what Kolmogorov assumed is something called an inertial range, that there is some decay to that. So I have this picture which tells you a little bit. So this is in wave number, which is equivalent to grid on the other direction. So at the large scales, independent of the grid size or the truncation, we don't care what happens. At the smaller scales, we have precise control. So this is what contemporary numerical analysis tells us. In between, we make the assumption that there is a bound, and this bound can be very rough. Any algebraic or non-algebraic decay is good enough. This bound can be very rough. If these bounds hold, as Kolmogorov hypothesized, then we have compactness. We are able to leverage this sort of physical insight into a compactness theorem for numerical approximations. Now, of course, there is a theorem. So if this theorem is true, under these conditions, statistical solutions exist, right? And you can construct them. But does it hold in practice? Okay, before that, what converges, right? We have this topology. So what converges are multi-point statistics. Earlier we had only one-point statistics, mean, variance, point PDFs. Now we have multi-point statistics, for instance the structure functions that I spoke to you about, spectra that I spoke to you about, multi-point correlation functions, and this is what is very intriguing. So these kind of simulations that I showed you, deterministic realization, nothing might converge, right? This is what but statistically, any reasonable quantity that you write down, even multi-point statistics, as many points that you want, the theorem says that there is some convergence to that, right? This is sort of striking, and at least to me. Now, is it true in practice? So here's an example: incompressible Euler equations, similar to the shear flow. This is what we call as a flat vortex sheet. So we have some oscillations here. This is the horizontal velocity, the vertical velocity, and there is some statistical nature to it, which is represented by the mean here and the variance here. So here the vorticity is an unsigned measure. So there is no theory for this before, but remember that we had conditions on the structure function on scaling and with conditions on the spectrum. Are these met by this simulation? So here's the computation. So these are the structure functions. As you can see, they are very nicely scaling, and there's almost a straight line here, and they all bunch up together. So certainly the structure functions converge, and this is the spectrum. So this is the, as you go here, it's a wave number, and these are the different resolutions. So as you can see, for 1024, for instance, in this range, this is the dissipation range. Here we have precise control. Numerically you don't see that because of round off errors and so on, but in this range we have completely uniform control. So by my theorem and based on this computation, you would expect convergence, right? But how am I going to represent that convergence? Remember that I have this weak star weak topology. Because of time continuity, I can just look at time snapshots. So convergence in weak topology on probability measures implies convergence. This is metrized by the so-called Wasserstein metric, or earth movers distance. It's a very popular metric on measures, but this is a metric of measures on infinite dimensions, so we can never compute it. But remember that we have this characterization where infinite dimensional measures have these marginals, finite dimensional correlations. So convergence here implies convergence. This is a small theorem, implies convergence for the Wasserstein metric at the level for the correlations. So for the first marginal, we have neat convergence. For the second marginal, this 2-point correlation measures, this metric we have very neat convergence. For the 3-point marginal, we have very neat convergence. So 3-point marginals means 3-point correlation functions. The whole measure converges. So this is a dramatic form of convergence, right? That you have all possible correlations are converging, at least to the third degree of correlation. This was an example of illustrating this. Here's another example. This is called the sinusoidal vortex sheet. for incompressible flow. So this is the vortex sheet here. You see the horizontal velocity, and the point about this is very interesting. So here the vorticity is a sign measure. So there is a sign here. The theorem of Delors applies. So there is a existence, global existence. But however, there was no numerical convergence of numerical methods proved in the last 30 years or so. This was solved by Lanthaler and me recently. We proved this, that indeed there should be convergence of the spectral method or spectral viscosity method in this case. But this is what happens. Even though I know that there is a proof of convergence, what you see here is the formation of vortices at smaller and smaller scales as before. So this is a single deterministic simulation, and the vortices are in different positions, different locations, and certainly the convergence slows down with time. I'm sorry, this is too small. This is initially very nice convergence. At a later time, the convergence is slower, and ultimately at time t equal to 1, it completely flattens out. So even we know that there is convergence, we have a theorem about it. The rate is possibly very slow, or there are some other mechanisms which prevent us from doing that. Okay, but let's look at the statistical solutions. Remember, structure functions, they are very nicely scaled and are convergent, and the spectrum is very nicely uniformly bounded here. So clearly the theorem applies, and you see that. So if you look at the mean now, remember that the vortices were in different locations, but the mean value is just two very coherent vortices, and also the variance is very neat, right? So clearly to the eye they converge, and when you do these calculations in the Wasserstein metric, there is some issue with statistical error, but in general you see this very, very neat convergence. So even though the deterministic convergence is proved, we don't see in practice. On the other hand, when you look at statistical quantities, there is very neat examples of convergence. I like this example because here the initial data is Brownian motion or fractional Brownian motion. So fractional Brownian motion, this is Brownian motion, looks very rough, but this looks even rougher because it's fractional Brownian motion with a very small Hurst index, 0.15. And this, the initial data here is in a class which is not covered by any deterministic theory because these don't apply. The vorticity is very nasty in these cases. Nevertheless, our theory works fine. The structure functions, and look at the spectrum here, it's completely very, very neatly bounded, and you see the very nice convergence in the Wasserstein metric for the 1-point correlations, for the 2-point correlations. So changing the perspective completely changes the situation as far as these objects are concerned. Compressible, so this was incompressible, right? Compressible, you know this example very well. There is convergence of the mean and variance. The structure functions converge very nicely. So in particular the scale, there are straight lines, and now I plot to you the 2-point PDF. So I pick 2 points and look at the probability density function. These are 2 different points, and this is a sequence of grids, and you can clearly see that it's the same object, right? So there's very neat convergence. It also can be measured in the Wasserstein metric. Here's another example here, Rickmeyer-Meshkov problem. So this is the density. There's some uncertainty in the bubble location, and the point about this is that you have very strong shock waves and they come back because of periodic boundary conditions. So now you can see that over a sequence of grids the solution becomes rougher and nastier and nastier. Of course you don't have any deterministic convergence, but when you look at the mean or the variance, very neat convergence. Structure function converges very, very neatly, and once the structure function converges, then everything else is supposed to converge. And you see that, for instance, with the Wasserstein metric, you have the 1-point marginals, very neat convergence, as it is for the 2-point marginals. So and we have tons of numerical experiments. Every experiment we have tried, the theory fits, and we have not found any exception so far. These are the probability density functions. So fine. So this is very pleasing in some sense, that by changing perspective, we are able to do much better than what was known before. However, what is also striking is the number of open questions, right? So in particular on the theoretical side. So what are the open questions? Remember that I have a conditional global existence. As long as the scaling assumption was satisfied, then I have global existence. But I have not been able to prove this, even for well prepared initial data, despite some attempts. I am hopeful, at least in some special cases, to be able to do that. What I am more hopeful is that we can relax scaling, because this, even though it seems to be realized in practice, maybe this is not a natural assumption. Maybe there are some other mechanisms where you can. So existence is something I am confident is possible. The harder question is that of uniqueness and stability, because now we don't have this generic issue, right, where we don't have enough moments. That's not the issue, but statistical solutions are weak solutions, or entropy statistical solutions are entropy weak solutions, where things are a Dirac, and we know weak solutions are not unique. So statistical solutions may not be unique. They're unique under certain conditions, for instance for scalar conservation laws, and the entropy condition is highly non-trivial. It's based on some convex splitting that is induced by the Wasserstein metric. For systems we have weak strong uniqueness in a very strong sense, but in a general case, if you don't have a classical solution, we don't know what happens. So there are many theoretical questions. However, this is what gives us hope. The hope is I repeat the same experiment. I change, for instance, Kelvin-Helmholtz, or maybe this is this flat vortex sheet from Incompressible Euler Equations. I change the amplitude or type of perturbations, and then I take smaller and smaller grid size. This is the 1-point correlation marginal, 2-point correlation marginal measured in the Wasserstein distance. These are completely stable, they converge to each other. Similarly, if I change the scheme, so one is a spectral method and the other is a finite difference projection method. Even the higher order correlations, we compute the same things. So each time we are computing, we are certainly seeming to compute something which is very stable. The question is, what are the selection principles? Additional selection principles than statistical solutions. What are these? And this is still quite exciting and still quite unknown. And in the remaining time that I have, which is I don't know how much over time I am, but maybe for 5 minutes I'll talk about the computational challenge. Okay, and the computational challenge is, so we have convergence, we see this convergence, we have theorems about that, but the point is it's expensive because our underlying method is Monte Carlo. As many of you know, Monte Carlo converges at square root of the number of samples, so you need a lot of samples, and the point is each sample is very expensive. How expensive? So this is a 3-dimensional simulation, because this is what we want to do, right? I want to do this in 3D. So 1024 cubed, and this is a code that I developed for many years. Even when Ujjwal was in Oslo, we were in the process of developing this. 10 years, we have access to a very powerful supercomputer, Peace Daint, in Switzerland. It's number 6. It's the most powerful supercomputer in Europe. But even on this, a single simulation will be 3000 node hours, but we need 1000 simulations, and that, if you look in dollar terms, is 1.7 million US dollars. That's the expense for a single simulation. Okay, this is even in a rich country like Switzerland, we can't afford this. So then I set up this challenge to my students that we need a speed up of a factor of 100, because if this was 17,000, it sort of is in the right ballpark. So the first achievement in this regard was by my PhD student Shetil Liye, and he realized that the reason why we are doing badly on the supercomputer is because it's all the computing power comes from GPUs. Our code was a CPU based code. So what he did is that he designed a custom made highly efficient multi-GPU code, and there are many nice features of it. It has very good scaling, it scales to all the nodes that we have, excellent memory performance, about 60% of or 70% of the, and some good petaflops performance. It's a really well developed code, and just by that, with the machine now, we got a speed up of a factor of 10 to 20. So remember, the challenge was 100, 10 to 20 is already done, but that's it, that's the limit. You can't get a factor of 100 from just the hardware, so we need new algorithms. But the point about it is that this has also excellent I/O input output and visualization support. Ramona Hall is a master student who did that, and I have to show you the same movies that I had in the screen because I'm really proud of it. So let me show you at least a couple. Okay, so this was playing before. Let's go. So this is Kelvin-Helmholtz compressible Euler. By the way, the incompressible Euler code is still being written, but this is compressible Euler in 3 space dimensions. There's a tube and there's a shear across the tube, and then this is a single sample, but it's at a very high resolution of 1792 cubed. So 1792 cubed, that's a lot. Oh, what is this? Sorry. And then this was the same picture that you saw in the video. You can see that the reason I am proud of is that we can do a 1792 cubed simulation. It looks very impressive, and the point is that this was done on 343 nodes. So it's quite intense in terms of the number of flops that we have used in the simulation. It's very complex, as you can see. Lots of small scale features are being formed, and hence useless, right? Because remember that individual samples are not computable, so in the sense that I just specified. So what I'm going to do is to go back to the talk, and then, but our convergence theorem has nothing to do with 2D or 3D. We have to check structure functions, we have to check the statistics and things like that. And when we do that, so this is a single sample. So as you can see, this was 256, 512, 1024, just the density keeps on getting more complicated. You don't have any convergence. On the other hand, when we look at the mean and the variance, let's see, let's visualize the mean. And this is the first time I sort of show anyone a visualization of the mean, and the mean is with 512 samples here. It's very hard to do this because the file sizes are big, so we have a neat way to visualize statistics now. So you can see this is the mean, and remember that you had this very complicated individual flow, and this mean is much better behaved, right? You can see that it evolves in a much more regular manner, which is not surprising because statistical quantities have better behavior. And this was the evolution of the mean. I have similar video for the variance that I'm going to skip, but let me show you the convergence plots. So this is the mean, boring but computable, right? And this is a very neat convergence of the mean. Variance, very similar, slightly worse rate of convergence, but still computable. And remember that underlying this are the structure functions. So these are the structure functions up to 512 cubed. They seem to have a very nice scaling. They also converge. And this is a Wasserstein distance. So this is a Wasserstein distance for a 3-dimensional flow in the infinite dimensional probability space, realized as marginals on the 5-dimensional phase space and 25-dimensional space in this case. You can see that there is very neat convergence of these objects. And in fact, remember that correlation measures are nothing but PDFs, 1-point PDFs, 2-point PDFs, and so on, and we can even visualize that. So this is let me try to show you. So this is 1-point PDF at one point. This is the movie. This is a 1-point PDF at another point, and this is the sort of the correlation between both of them. So it just means what you learn is dynamic behavior, very rich dynamic behavior. So this is let these guys just run. So particularly look at the 2-point correlation. It's really evolving, right? It started out with something, but it's all over the place in a very nonlinear manner. But the point is now we can compute them. So there is a theory which says that this is indeed a correct computation, and we can even visualize them. So you can even see how the probability density function, or the 2-point probability density function, in this case only for the density itself, how these things evolve. So these objects are computable, they are even visualizable. So you can see that, and this goes on. This looks a little bit like a video game, but sort of. Now this is I end with another example. Yes. So this is the Rickmeyer-Meshkov in 3D. So now we have shocks coming in from all directions and hitting this bubble, and you can see that we are just visualizing it from an iso volume. So now you can see as we refine, this object here becomes very complicated, this ball here. There is no convergence, needless to say, and this is the mean. Now remember that these have shock waves, so the mean should have that. Very nice and computable. Similar things for the variance. Structure functions, they all cluster together, converge very nicely, as does the Wasserstein distance. So whatever we saw in 2D is transferable in 3D at a considerable cost, right? Because remember that we only got a factor of 10 to 20, not 100. So because of that, we have not been able to do this at 1024 cube. That's the next step. Nevertheless, it's incumbent upon us to find another alternative, because even this is expensive, and we have a bunch of alternatives because we need a speed up of a factor of 10. And we have a bunch of alternatives here. I don't have the time to describe them, but let me just give you the keywords. One is multi-level Monte Carlo. Deep Ray, who was a PhD student here, Praveen and me, and who is in the US now, he was instrumental in some of these problems. And for many problems, we observed speed ups over the Monte Carlo algorithm of factor of 100. But for the very difficult ones, like these chaotic ones, we got a much more moderate speed up of 3 to 4, 5, roughly 5. Not there yet. And this was by doing time averaging. Quasi Monte Carlo was another example where you sample, instead of random points on low discrepancy sequences. Again, we observe better convergence rates for many problems, but very modest ones for these very chaotic problems. And the latest element in this is, of course, neural networks, artificial intelligence, a bunch of people working on this. And again, for several problems, it's also very challenging. There are new kinds of challenges. For several problems, we found a speed up of 10 to 100 over MLMC. So this was even amplifying the speed up. It's not yet clear whether this will work in this most chaotic regime. So at least computationally, I'm much more confident that in a couple of years, we'll be able to breach the barrier, that this will be 100 times faster or even 500 times faster, and we can do this kind of simulations. I'll end with this Venn diagram, which sort of summarizes, because the question was how do we fathom or understand fluids, right? So certainly we can't do it within the framework of classical solutions, because this is something PDE, the first PDE course, you learn that. Then for a long time the belief was that it could be done within entropy or admissible weak solutions, and clearly now with non-uniqueness and so on, non-computability from all sides, we realize that this can't be done. So then of course one could expand the net and go to measure valued solutions. Here we have global existence, we have computability, nevertheless there is no uniqueness. So a lot of the work in the last 5 years that I have done is that I pruned down this set and got it down to statistical solutions. Statistical solutions nevertheless are generically non-unique because they include entropy solutions. We know computationally that we are computing something which is much smaller than statistical solutions. It includes classical solutions. This is a proof. What I know is that there is a non-trivial intersection, it's not weak solutions, there are genuine measures. But further characterization of this set, further work answering this question mark here is sort of the key theoretical challenge. Computing it is going to get resolved pretty soon. So this is where, at least in my research program, I visualize how we understand fluids to be. And of course I finish without thanking my collaborators, would not be feasible. So let me thank them. So Ulrich Fierholm, he was a former PhD student of mine who is a professor at the University of Oslo. Ramona Hall, she is a master's student who is just starting a PhD. Samuel Lanthaler, a lot of breakthroughs happened during his master's thesis. He is now writing his PhD thesis. Keppeli was a former postdoc who worked a lot on measure valued solutions. Kjetil Lie is sort of the computational spearhead of our group. It's he who has done this big simulations. Roberto Molinaro works on some aspects of machine learning, PhD student. Carlos Perez on incompressible flows, the computations. Deep Ray, I'm particularly proud to have him as a student. He was from here, he was a PhD student here. He's a postdoc in the US now. He works on the machine learning and multi-level Monte Carlo. Eitan Tadmor, long-time collaborator and mentor. And Franziska Weber, who is a former postdoc, former master's student even, who is a professor in the US at Carnegie Mellon. So these are the people who worked with me, and we have come to this stage thanks to their help. So thank you very much for your attention.
So thank you for this insightful talk. So now any questions or comments?
Yes.
Here is convergence of statistical solutions. So that's like a law of large number kind of thing. Would it be relevant second order central limit theorem fluctuation?
Yes, absolutely. Absolutely. This also numerically this would make a lot of sense, but theoretically it makes a lot more sense because not just the second order central limit theorem, but more like a large deviation, sort of concentration inequalities. So one of the ways in which we are trying to characterize this small set is by using some concentration inequalities. But at the moment this is sort of a premature research project, but I'm hopeful that this will help. There is some concentration of these objects, and this is what we see in numerics. So this is very relevant for sure. But it's not, we have not computed large deviations yet. That might not be so relevant. Concentration might happen, and this might be very relevant. Yes. Yeah. Well, this is yeah, because this first of all, statistical solutions are a way to characterize turbulent fluid flows. Right? This is one possible way. They were actually introduced for the Navier-Stokes equations much before, in the 1960s, 70s even. For the Euler equations, that was the formulation didn't work because it assumed some regularity. So they are meant to describe, these flows are what you see in practice. So when you see smoke coming out of a chimney, you see this kind of whirls and you see this kind of eddies and so on. So the whole point is to explain physics. Means this is sort of and the experiments, you know, physicists when experiments, they measure the spectrum, they measure the structure function. It's sort of fascinating that those objects are precisely the central players in a mathematical description, mathematical theory of these objects. So that's sort of the correspondence. So the model is always Euler equations and Navier-Stokes equations. So this is. This is okay. This. I understand your question very well. So there are several ways in which those are very hard questions, right? Because of course, if you think in a classical deterministic setting, everything is Newton's law. Means when I'm talking about the flow of air, it's Newton's law, right? You can write down Newton's law, lots of interacting particles. You can add some noise there, presumably I don't know what kind of noise, and then you pass to the infinite particle limit. This will work if you have smooth solutions, right? Yes, yes. So there are things like shell models and vortex models and so on. We have not studied that, but that will make sense once we know that somehow the limit behavior is understood, right? Because then maybe that's a physical realization of this particular limit. This is a way to tackle the question. It would be to ask what sort of, and it will be particularly relevant for some high order physical questions about energy conservation, about energy dissipation. Can you explain these probability density functions physically? Means this is the question, right? I clearly can't explain them. I can only compute them, and I know that the computation is correct because of the convergence theorems. That would be fascinating. But first order requirement for that is we understand the limit better, we understand it mathematically better, because otherwise it probably is not going to make a lot of sense. So clearly that's necessary, but it's far in the future. We are nowhere close to that, right? Yeah. This is a very good question, right? Because so what you're asking is a homogenization question, right? Because what is the meaning of consistent now? Because the solution, even if you start, let me look at some pictures and then I can show you. Let's go to the two-dimensional. Okay, let's start here, for instance. So even if your initial data was a Dirac measure, for instance, by just letting the probability, the initial uncertainty smaller and smaller and smaller, your solution will remain, this will be your PDF. This doesn't change. This is it is not a function of my initial perturbation is tiny, it's less than 1% of the mean. But even if I had taken 10 to the power minus 5% of the mean, I would still get the same probability measure. So the initial data itself, so for a deterministic initial data, the solution is a PDF or a Young measure or a probability. So in the space of probability measures on functions, even if you start with the Dirac, you can sort of broaden it out, right? So the equation, what does the equation mean then for this object, right? The equation can only be the equations that I wrote for the moments, which are clearly satisfied, because my Lax-Wendorf theorem tells me, which you taught me many years ago, it tells me that that it finally converges to these moment equations that I wrote down. Now the question is, if you take averages, can these moment equations be closed? Because that would be the logical thing. That I don't know, because that's a very hard question. My answer is no. I think approximately yes, but exactly no. I think you need infinitely many moments, but yeah, it's just a speculation. There were some people from Bombay, right? Maybe they, I saw them at some point, but maybe.
So, Siddharth, thank you very much for the interesting talk. Yeah, so we want to thank Professor Gowda for accommodating us, our request, first of all. And a couple of questions from our side, if you can hear us clearly.
I can barely hear you, so let's try nevertheless.
Can you hear us now?
You don't hear it.
Yeah. Okay. Yeah, so this theory of statistical solutions, are they related to this regular Lagrangian flows which Ambrosio does for the ODEs, where they are also trying to do solutions as measures on the flows associated with the fields, right? So this is...
I understood your question. Yes and no. One way to think about, and I know that theory maybe not very well, but I know it okay. So the point about it is that this makes sense in one particular context where if I have a flow field and then there is some sort of a passive scalar that is being invented by the flow, then you can have this sort of, or even active scalar for that matter. So then for home, one of my students, he has tried to characterize this in terms of the Ambrosian characterization of vector fields, ODEs driven with rough vector fields. But I don't think, personally, I don't think that will lead to anything, because we're not exactly in that situation, right? We don't even know if the vector field itself makes sense. It exists in this strange sort of as a probability measure things. I'm not sure if that will really lead to, maybe it can answer some high order questions like what was asked here, but I doubt if the basic questions of existence and uniqueness could be answered. I could be wrong. Now they have disappeared, is it? Okay, so I was just speaking to it.
we can hear you. I think they are.
You have to talk in this.
We can hear you, and we.
This is disconnected.
Yeah, they did.
Did you hear my answer? Now they. Okay. Can you hear us? They don't.
They are frozen.
Yeah.
Okay.
I don't think so. I certainly can't hear them, so then either we stop or we wait. Someone else can ask a question in the meanwhile, if there is another.
So just a quick question.
Yes.
How do you encode concentration effect in your solution?
This is, we talk about it. This is several hours answer, right? No, concentration of the measure. No, this is the whole point, that once you have this uniform diagonal continuity, you rule it out. So, so once you have in space, you rule it out, because once you have uniform diagonal continuity, it provides you some strong control on oscillations, which in turn you can. It's not hard. It's 2 pages of calculations, which shows you that you can rule out concentrations also. So the Young measures that I am getting, even though my test functions are not compactly supported, these functions are allowed to grow. I had to cut many things, right? These are technical 60-70 page papers, so I had to cut many things. Even this, so you don't have concentration effects. There is no L infinity bound, but even with the energy bounds that we have, you don't have concentration effects if you have this uniform diagonal continuity. This is a lemma.
Is it not a strong condition? In practice, you do encounter.
Not in these flows. There are these examples that were built by Diperna and Maida with very irregular flows where you artificially construct oscillations, concentrations, but not in these flows, because this is what you don't see in the numerics, right? So in a way, yes, you can say that this is a stronger condition. That's why it needs to be proved, right? Because so it's sort of, so concentrations are, if this condition holds, concentrations are ruled out. So there are no concentrations. But the point is, these constructions that Tippern and Maida made, they are not based on any approximations. They are exact solutions. Navier-Stokes does not have them. 2D Navier-Stokes is very nice, right? So it's Navier-Stokes doesn't have them. So I'm not sure if these are relevant obstructions, but I could be wrong. Are we? So we've lost them. Yes. Now you are asking harder and harder questions, right? Because large time behavior, first we have to get small time behavior, because that is what is uncertain. Large time behavior is going to be very, very interesting, because the answer would be the same, right? Because once you construct, this is a program, that's large time behavior would be a future step. So once you have small time behavior, finite time behavior, then you have a sequence of measures again, probability measures and functions. Then you take the limit t equal to infinity, and if these conditions that I wrote down, they all break down, by the way, in the large time limit, because they all depend on the finite time. Whenever I do estimates, somehow you take the final time out. It would be interesting to study if, at least numerically to start with, what is the dependence with respect to time, right? What is very interesting is that even though we have a dissipative system, because we have numerical dissipation, the things persist for a long time, which is what is experimentally known. This is Kolmogorov's 7th law or something like that. But so this is quite fascinating, but none of the estimates work. This is as simple as that, because we are lazy, right? We only care about finite time behavior. So each time we have a finite time, we estimate everything in terms of so with long time behavior, certainly not with these tools, for sure. This is not possible. Absolutely. Anything, I agree with you. But what is okay, this is the reason why I didn't show this, but we have of course done this long time behavior numerical studies, and what we observed is truly fascinating. So we characterize somehow the regularity, stochastic regularity of the flow by the exponent of the structure function. So the fractional Brownian motion, for instance, the initial exponent is the Hurst index, right? Then you let it flow, both incompressible and compressible. In both cases, incompressible shocks come in, right? And the shocks are going to kill out some of the small scale features, and you see that there is a very nice gain of regularity of the structure as measured in terms of the structure function. To prove it would be great, and this happens, the sort of the limit in terms of the exponent of the structure function, let's say statistical steady state, much before the deterministic steady state. For each sample is still evolving, but the statistical properties come to equilibrium. What is even more surprising is that for incompressible flows, we observe the same behavior, that there is no apparent mechanism for regularization, but then you just let tons of fractional Brownian motions run, and you see the behavior of the structure function, and you definitely see a gain in regularity as time progresses. So somehow turbulence is also able to produce some regularizing effects. What's fascinating is that even though, so if you have shocks, like if you have just a vortex hitting a shock and going away, then the structure function, particularly in the high LP spaces, this goes down because the BV norm is there, so it goes down with P. Whereas for if you have turbulence and shocks together, it has very interesting behavior. There is some steady state which is better, we have better regular. These are really interesting, fascinating high order questions, and I can show you some of these results, not now because I can show you, and you'll see that there is some strange, many new things which come out when you look at long time behavior in terms of statistical regularity, and this, to prove it, is yes, we have that. I think, well, from numerical evidence, I don't have a proof, maybe we can discuss that. From numerical evidence, it goes to the N wave. Yes, the statistics is completely consistent with what was, the formal calculation is very easy. because you just look at how many shocks are there, you count them, and then they sort of dominate the statistics. This was done by Sinai, right? This is his famous result on Burger's equation. Yes, also we are looking at periodic boundary conditions, yes. But then you see that the shocks eat up the small scale features. This is not surprising. This is not at all surprising. What is surprising is in incompressible flows or in multi-dimensions, shocks are our friend. Shocks are good. They organize the flow. The problem is turbulence, small scale features, because when shocks are there, they clean up small scale features. So there is this fight between these two things all the time. I think we give up. Huh? Yes, yes, you decide. You are the hosts.
You have waited enough.
So if there are no other questions, we thank Professor Mishra again.
Thank you.
Now I request Professor Gaurav and Professor Adimurti to present Professor Mishra.
Okay, maybe I just want to say one final thing, just 1 minute, because of course most of all I would like to thank Professor Adimurti because in person, because he was my supervisor and he taught me. I certainly don't do that with my students, but he used to spend 3 hours every day for the for 2 weeks during the winter during my first year. Yeah, I think Sandeep remembers this, right? And we would be desperate to go and play badminton, but but 3 hours lecturing in front of him. Rarely does a supervisor give that kind of time. I certainly don't give that. And if I tell my graduate students, that's why I took out the mic, because this they won't be they will. This is sort of insane levels of commitment and dedication, and I'm really grateful to you for that. Thank you very much.
No, it is very difficult for me to tell anything because I'm not used to this one. But certainly, I'll tell you, he joined in the first year, integrated the PhD program between IISc and TIFR. He was in the first batch. There are 5 students, 6 students are there. 2 of them are very good. The other 4, one went to US, Anusha, and the other 3 they discontinued, right? So out of the 3 students, they're thrown out. So the first 2, the 2 remained was the really bright students. One is Saugato, who is now a professor at IISER, Calcutta. The other person is Siddharth. So there was a competition between these 2 people, Siddharth and Saugato. Even now Saugato feels that I should have become like Siddharth. Okay. Anyhow, okay, one thing I would see, there was a Saugata went to Switzerland to do his PhD. In fact, he went to work in DPFL. Dakroni asked me whether there is a very good student who can come and work with me. So I asked Saugata whether he is interested. He said, yes, I would like to go. And he was, in the beginning he hesitated, then he finally said, okay, I'll go and work with him. Second one is that there is one German professor was there. He was visiting. He also wanted to have one student. So I asked Siddharth, are you interested in going? Siddharth suddenly said no. Okay, and he stayed back. So Saugata returned from Switzerland. Siddharth went and took the chair in. I mean, he at the age of 30, he became the chair professor at ETH. You know, I'm really proud of him. Okay, thank you. That's all.